All right, seems like we have everyone. Yeah, am I audible, first of all?
Yes, I can hear you.
Oh, perfect. Let me share my screens then. Perfect. Um, can everyone see my screen?
Yes.
So we have a notebook here. Hopefully everything is working as expected. Um, yeah, do you see my terminal in my VS Code window? Just to make sure everything is proper.
Yes.
Cool. Um, Welcome everyone. Welcome to the machine learning and AI training. My name is Thera Gandhi. I'm going to be taking you guys through the first day. Essentially, Matt Bauman was supposed to be here. There was a very last minute conflict in his schedule. So he might still join later on, but for the time being, I'm going to be driving you through some of the training aspects that we have to cover today. Apologies for the delay. There was a bit of a conflict in terms of the timings and such. So just before we get started, let me give you like a really quick rundown of what we're going to cover. So the first thing that we want to basically go through are the basics of what make machine learning tick. And another thing that we're going to be focusing on are the different toolings that are available in the Julia ecosystem, especially maybe not people would have heard of things like Flux. So that's going to be another area of focus. And just before we get right into it, let me go through Julia Computing. Julia Computing is a company funded by the founders of Julia the language. Hopefully everyone is somewhat familiar with the idea of Julia, and we'll go through some of the basics of Julia that we will be using throughout this training, right? And more than not, I wanted to talk a little bit about. This was founded essentially by the founders of the language, seeing that there was a bunch of demand for Julia in the enterprise world essentially. And I really appreciate you guys sticking around and like coming over for the training, and very similar stories that we find when people actually do attend these trainings and such across different domains. We find that people have been using Julia in many interesting ways. So I really encourage you guys to check out the case studies on the Julia Computing website. So everything from managing drones to deliver medicines to actually doing, large scale machine learning, as well as financial marketing predictions and such. So you would find Julia's use in a lot of widespread domains and such. And this is one of the beauties of the language itself, right? It's designed to work around these very large numerical workloads and scientific workloads, but do it in a manner which is very efficient, which gives it its speed, really. Um, let me also uh, go through some of the things that we would focus on in specifically the training. So hopefully you can see my screen here. Let me know, shout at me if you have any issues getting started, right? But one really quick tidbit that we do have is that uh, hopefully everyone has downloaded either the zip file or the Git repository for this training. So this has all the data and the code that we will need. Um, oh, someone cannot see my screen. That's interesting. Um, hmm. Is that for everyone? Can no one see my screen right now?
No, I can just see it just fine. You're moving your cursor. I can see the terminal window.
Yeah, I
Can see it.
Okay. Roberto might need to check something with his settings. I think. Um, yeah. So all that is fine. No worries. We'll sort that out as things progress. I've shared the link again in case anyone needs it. It's the link to the materials that we will need throughout this course. And I want to also remind that we will in fact have some time for Q&A breaks in the middle. So let me know when people would like some time off just to gather their thoughts and maybe do a few exercises. So one of the things that we wanted to work on specifically in machine learning is this concept of what it is, right? So the simple fact here is that we have a bunch of data around us, and this data can be in many different shapes and forms, right? It could be financial data, it could be images, it could be very unstructured documents, um, or very large simple matrices, right? So especially when people are trying to work on some very scientific problems. And one thing that is very common between all of these tasks is that we want to figure out certain interesting properties from the data itself, right? And obviously, there's many different areas of study which are dedicated towards finding specificities of the data sets. But in many cases, what we want to do is we want to have the machine itself tell us what it can glean from this data set, right? And this is where machine learning comes into the picture. The core concept is that we have all of this data and we want to fit this arbitrary function essentially, this model, and we want this model to represent this data set as best as it can. And this is a bit vague necessarily because we want to introduce these concepts fairly simply and then create the motivation that we need to actually go further. So one thing that we always focus on is the kinds of problems that people are looking to solve, and that's a very effective way of seeing how these things actually mature. So one of the tasks that we will be dealing with in this training is simplifying how to classify images. And specifically, we'll be interested in classifying the images of different fruits, so apples and bananas. We want to create a model, a machine learning model, which is essentially going to be able to classify these fruits. And we want to do it automatically. Um, but we don't just want to use an API, which is fairly simple. We will see how this tooling exists, of course. That's how a lot of machine learning in the real world works. But we also want to understand the intuition behind why we're building it like this, right? So this training, I'm going to be splitting it between showing some code in this VS Code window, some plots, as well as this my bad, Pluto notebook. So Pluto is another one of those Julia projects, which is basically revolving around reactive notebooks, and it's what all the cool kids are using these days, shall we say. So it's very similar to what people might have seen in excuse me, with Jupyter, but it's written from the ground up with Julia in mind, right? So it's one of those new tools that is fun to play around with, and it's definitely very useful for interactive use, something that we will see comes in really handy. However, it may not be the ideal tool for all use cases, right? So we don't really want to fit a square peg in a round hole, essentially. But in in the case that we're trying to do right now, which is very pedagogical, it makes a lot of sense. You'll see. So one thing that we want to talk about as well is some of the basic syntax of Julia as well. So right, um, let me start off by saying that everyone is familiar with what an apple looks like, and we generally just want to load up an image, which can be a JPEG, PNG, whatever, and we use the images module to do that. And when we load it, we see that rather than giving us anything which is very daunting or scary, we get back this image itself, right? This is rendered for us beautifully so that we can actually make head or tail of what's going on around us. Um, so this very much does in fact look like an apple. This looks like a banana. So I guess we're in good stead there. But let me ask Julia about what it thinks the type of this apple-looking thing is, right? And we see very quickly Julia responds with array of RGBX. So this is a bit weird, right? Because normally what we're used to seeing is an image is an image type, but frankly, how we see in the Julia world, and as different abstractions for machine learning grow, we find that images are just arrays of numbers essentially, right? And in this case, we have this odd looking RGBX thing. Usually, if I ask Julia to make me an array, I can do something like 1, 2, 3, and 4, right? So this is just very basic syntax. Apologies if you guys are already used to it or not. So just so that everyone's on the same page, really. So when we gently construct an array, we would do something like this. So this is basically saying this is the first row, this is the second row, delimited by these semicolons. And when I see the type of it, Julia gives me the type right there, and it says that it's formed of these int 64s. It also tells me that it's a matrix, but the interesting part is that it tells me the type straight up. And in the case of the image, I'm told that it's this RGBX looking thing rather than an integer or a floating point, as I would imagine, right? And the reason for that is that we generally do wonder, like all of these images, they have these they're like pixels, right? So every image has different components to them. So if I were to say drop all the fields of what this RGBX looking thing is, let me do that really quickly. And I get it has these different fields, R, G, and B, so red, green, and blue, and something called this alpha dummy thing. We don't really have to worry about that. But people who are interested in image processing would definitely be familiar with the alpha values of an image. So that's really cool. It means that not only are we able to get our types right, an image is just a bunch of pixels. We can see it rather than have it displayed in that crude manner, as well as we can reason about it, right? Notice how I picked out the logical index of the apple straight up from the apple type, right? And this means that we can. This is basically trying to show that we can use it as any other array, and that's really going to come in handy. So in fact, an image is a 2D array made up of these colors. So we use the colors package, which exports this RGBX type, which acts as a pixel, and it means that we can render it, but more importantly, we can state general about the kind of object it is. Rather than saying it's an image, we know it's just an array of pixels. Now, this is going to come in really handy because one of the tasks in machine learning that we'll see is simply the fact that we want to understand how to reason about these pixel values, right? So what does it mean that you know, the R value is something. So between 0 and 1, what does it mean if it's you know, it's zero point 0.3? How does it matter in relationship to the corresponding G and B values, or how does it matter corresponding to the surrounding pixels? How do you find features that are important so that we can take them out and use them to manipulate our data sets such that we can differentiate between these things properly? Um, Also, just let me know if something is not clear, and I'll be happy to clear things up. Feel free to unmute yourself. Feel free to drop something in the chat if it's not clear. Um, all the materials are right there in front of you. We have a bunch of literature around to help you go through the the code as well. So the code that you see here and the text that you see here is exactly the same as I have here. So feel free to read either. Um, yeah. So one more interesting thing that we want to see here is that we have a 40 comma 60. So this thing gives me another pixel, right? But that's not quite what I'm interested in. What I really want to know is the redness of that pixel. And all I have to do is call the red function over on top of this. Um, Excuse me just a moment, and let me close some of these tabs up. Right, this is much better. Um, Oops, I wanted fill there, not A. That was my bad. So one thing that we see here is that we get the value of the red pixel straight up. And this is very handy because now we can call upon the different channels essentially, the different channels very easily and directly. It has this any uh, notation there, which is a bit weird, but we'll see how we can just pass it into a place 64 bucket and get the place 64 value of the bucket. This is standard in Google. However,
Excuse me, looks like your audio is broken. I can't hear you.
uh, now the fun thing about machine learning really is that we get to play with all of these statistical components of our data set, right? So like not only are we interested in the red values of that is calculated. Okay. Um, Let me reconnect. Okay. Is that right? Mm, Let me just disconnect and reconnect with the situation that we have. Sorry for that.
Sorry about that. Please, hopefully it is better. Um, yeah. Can everyone hear me fine now?
Okay. It should have picked up now. Okay. Okay, yeah, better. Cool. Right. So what we can see now is that we can replace our RGB components with real numbers, right? And that's going to allow us to, not just see that these are in fact real values that we're dealing with, but also understand that, we can play around with different aspects of the image. So for example, I'm going to create an array which will just calculate the mean of the red, green, and blue values for the apple and the banana object that we just loaded in. Um, and as you can see, we have the different RGB. This column corresponds with the apple, and this for the banana. And what we see are the mean values here, right? So that means that we can now play around with the apple and the banana object just as if it were any normal array, which is very helpful as we move forward. Because what it now means is that rather than having to deal with um, weird types, we can now also reason about it in terms of in variations that we do understand. However, the one really good benefit of Julia is that we try to keep most of the code that you see absolutely general, which means that you really don't have to worry about these types in practice all that much. um, so that's very handy. So this is just putting out different red values um, for a corner pixel, as well as for the pixel that we chose earlier. So this pixel is probably within the apple, whereas this is outside of the apple. So what you would see here is very different from what you observe here, right? So this is the RGB value, whereas here you see everything is basically close to one, which basically means it's white, right? Because it's on the corner. Um, so one thing that we would want to do is we want to plot how red these things are. So let me ask people in the chat, and this is sort of like a meta exercise that I hope we can do along the training itself, right? And it's simply uh, when we say that we want to classify a banana from an apple, what is the first thing that comes to mind, right? Like, how would you identify an apple versus a banana? So this is kind of an exercise for the audience. So I'm hoping to get some um, input in the chat or however. Right. So the majority of the opinion is basically that we either use the color or the shape. And one thing that I've focused on so far is, differentiating it based on the color. Now, we would expect, an apple to be red and a banana to be yellow, right? Um, and we would definitely expect an apple to be redder than a banana, right? And which is why we're, pushing this redness, so to speak. Um, And now what we're going to be doing is basically plotting the redness of every pixel essentially uh, of this Apple image. So what you see here right now is Julia's broadcasting in effect. So let me give you a quick demo. So when I say red of Apple itself, I would expect to get a method error saying that Jira doesn't understand what to do with an apple or what the red of an array is essentially. So you see no method matching red of array. Um, but if I ask Julia what the red of this pixel is, it's happily able to tell me that, right? Which means that I can get the red of every element of my Apple. So this broadcasting operation, which is done by using just this tiny dot here, will apply this function over every single element, would apply it element wise. And as you see here, now it gives us something more meaningful that we can deal with. More importantly, we are now able to pull out the red part of the apple and store it in the Float64 format, which we'd seen earlier. And that's all well and good, right? Like that's ready for us to go. So now we have the red part of every pixel of our Apple image. And now we just plot it as a histogram, right? So we're going to plot, how many reds do we like? Um, what intensity of red do we see usually? Shall we say? Yeah, that's a nice word. That's a nice way of putting it, right? So if you get the mean of every single element, we see apparently it's 0.57, which is pretty red, right? And now I have a really quick, riddle for you guys. So as you can see, I have that, uh, really interesting, demonstration that we did, which was, well, an apple is red. um, I want to ask how red is a banana, essentially, right? And for that, I would do the same thing that I did for my Apple case right here. Um, take the mean of it, right? I want to do that for a banana. And what I find is while my Apple is at an average 0.57 for its red intensity, my banana is zero point 0.9. Now that's very weird, right? Because we don't see any red in the banana. So would someone want to hazard a guess about why that would be? So feel free to type in the chat about why you think that is. So this is very awkward for us, right? Because our job as machine learning researchers and scientists and practitioners is that we want to create these models which can very easily differentiate between different properties of these data sets, right? And the first thing we were thinking that we would use these features, the redness of the apple, to tell it apart from a banana. We're somehow not able to succeed right here. That's kind of awkward, right? So Gertie, hopefully I got your name right, says that yellow is coming from the red in RGB, and that is partially the answer. But what that would do is that would have a lower percentage of red because it also has to accommodate for other pixels. So basically, uh, the the uh, green in that, right? The green and the blue to actually come up with the yellow pigment. But what I'm trying to worry about right now is the fact that not only is it slightly higher, it is significantly higher, which means the the banana image is significantly more red than the apple image. And the real reason for that is, and as someone had pointed out very early on, is that we also want to be interested in the shape of fruits, right? Because right now, if you see, both these images are 100 pixels by 100 pixels. But since this covers a significantly lesser amount of space, there's a lot more white around it, right? And an RGB pixel is white when all the components of it are at as maximum percentage as you can go. So that pushes the redness of the banana significantly higher up and causes it to show up as looking more red to a computer, which basically is my long way of making the point that humans and computers understand data very, very differently. And it is very important for us as, again, ML practitioners to understand that and to put that to good use, right? Um, and by put that to good use, I mean we should be cognizant of the fact that we have to worry about proper trends in the data itself and not be subject to biases that we might bring in. Not only that, it means that we have to make sure that when we are developing our models, when we're doing our featureization and such, we are able to you know make use of the most the most varied features as we can. So this is a plot of the green of so if you would come back here, right? So this is the array that shows the RGB of the apple and the banana. So this is the mean values. And what we see, first of all, is that the redness of the apple and the banana is pretty close to each other, right? Whereas the the green pixels are not so much. The green pixels are fairly far away at an average, which does come up with a lot of different questions about how the data is actually distributed. But for the time being, to simplify the problem that we're dealing with, we can say that the uh, if you look at both the G and the B, we see a fairly good separation, but uh, G slightly more so, basically because the green and blue for the apple is fairly similar, but the delta between the green is more for the green in terms of the apple and the banana versus the blue. So that means that probably green is a better feature to differentiate between apples and bananas. Who would have thought, right? And rightly so, we'll plot that result and see if that is actually true. And what we find is that there is some amount of overlap between here, right? And that does give us a bit of caution in terms of how well a single feature is going to work when we're trying to do this at a very, very large scale. But it does mean that we can, for a very simplified model to actually learn the back edges of what we're trying to achieve here, we can use green as a pretty good stand-in to learn. Um, so let me ask right now: is everyone able to follow? Does that make sense? Something that you want done differently, repeated, whatever. I'll be happy to take that up. Cool. Seems like everyone is able to follow. That's really interesting. Um, Next thing that we'll then look at. So this is essentially the first notebook that you have here, right? Um, and a little bit more than the first notebook actually, because we also work through how we represent the data. Um, but I would encourage you guys to look up the tools notebooks a little more independently, purely because of the fact that we have a bunch of exercises in here that are very, very helpful to understand not just why we're doing things, but also to understand the syntax, the Julia syntax, so you can, apply it to your problems more readily. Some of this may seem very simple, some of this maybe not so much. Some of this would be implementing, exact algorithms that we, dictate, and other cases, it would be, a few more of these riddles essentially to figure out why things work the way they do. So I will be picking up a few of these tools notebooks just because there's interesting bits in it that I want to talk about. But by and large, we want to stick with the concepts in this one. So I'm going to be picking up our next notebook here, which is representing the data with the models, right? So one thing that we understood earlier uh, is that we can't really use the red value. And this is just us, accepting that, humans are just not that great at picking out the features. Um, yeah, very little to say about that because as we found out, we will now try to, go through what other options we have. So we do that with finding the green value. So now we want to basically understand the difference between how do we use this green value to actually pick out or uh, differentiate between our apples and bananas, right? So a green value for us, as we saw earlier, is just a float. It's just a floating point number. Nothing too special about it. But what it means is that when we deal with any other kinds of inputs, we have a good notion of what we're dealing with. So that's basically it. So one thing that I would want to talk about here is the difference between data and parameters. So essentially, in machine learning, what we always usually call the universal function approximate with the neural network, right? How does it really do that? And one of the reasons it's able to do that is because it uses the data itself to generate a function approximation which closely resembles the different facets of the data set itself in a manner that when we send it a data point that it has never seen before, it is able to generalize it well over the interested problem that we have. So I've said a bunch of things in here, right? First is how does it know? What does it do? And the simplest way of putting that is it does that through manipulating these parameters. Now, as you noticed earlier, I only had the green values, so you can think of that as either a matrix or higher uh, dimensional array, which has all the RGB values, and we can clump a bunch of these together, right? So this is my input essentially. My input is a bunch of these green values. Now I give it to another function, which can be my neural network, and the neural network within itself will have certain parameters. So these parameters, we usually call them weights and biases. So these parameters we'll see is basically how the neural network will basically use those parameters to generate an output. Now that output can be one of two things. It can either be a zero, and let's say I'm just making this up myself. Of course, in practice, it'll be different. So let's say a zero represents an apple and a one represents a banana, right? And in that case, I want my neural network to output a zero every time it sees an apple and a one every time it sees a banana. So that's my basic structure. I have inputs, I have certain parameters held within my neural network, and then I have some outputs. Uh, Fairly simple. Now, what I want to bring upon is this notion of how do we know that we're close to what our objective is. So we want to fit this data right in with our uh, you know with we want to fit our parameters to the data that we're seeing essentially. So this is basically learning. This is the process of learning. How do we do that? We'll find out in just a moment. But before that, let me bring up some visuals so it's easier to understand what we're trying to do here. So this is just a really quick demo of in Pluto. Whenever we want to deal with uh, very quick animation, so to speak, it's easy to just plot the kind of thing that we want to do, and based on that, we can see that I can move around this bar here, um, and give it a second, and we will see that. it will actually move around this little ball, so the scatter point. Oof, this is taking annoyingly long. I think I closed all the things here. Let quickly, yep, get rid of any open tabs that I don't need. This can go. Right. Hopefully everything else is held right in place. Yeah. All right. So we're able to see that we can move around our little ball, right? Hopefully that's helpful. So this is basically to say that, whenever we have certain parameters that we want to tweak in a function and see how that affects our output, we can do that. Um, Let me jump right here. So say I have a function, right? And I have a function which we usually call sigmoid function. And the reason we want to do that is basically look at, I want you to focus on this red line here, right? The square wave. So the square wave says that anything after zero, anything uh, is either one or zero. So our apples or our bananas, right? And this thing we can imagine is the arbitrary function that we're trying to fit. Um, and we want it such that it follows this red line as best as it can, right? Um, so right now it's at basically when w is 0, there's nothing, this is a straight line. But what we want to see is when we manipulate w, how this actually changes, right? So the sigmoid function is special in machine learning because what it tries to do, it creates. Uh, so this is the ideal curve that we want, right? Like for every banana, give me a one, and for every apple, give me a zero. But the reality of it is that at zero, what do you do? So there is a discontinuity in here, which means that it is not differentiable. Um, you might remember the concept of differentiation from high school and later. And the whole idea behind using a differentiable function here is that we are able to have these smooth transitions between different states that we want our models to be at. So this is a very simplified model which has just one parameter, the w, and the input is basically all the points from -5 to 5, right? And let's see what happens as I manipulate my w, as I move it around. So you can see it tries to move around as we're increasing w, and as I decrease w, it goes completely the wrong way. So this is sort of up to us to now understand that we really don't want this. This doesn't fit our curve well at all. So we'll try to move it in the same direction that we did earlier to hopefully get better results. And yeah, seems like we're getting there. It's still not pretty good, but as you can see, it's um, after these bounds between -2 and 2, we're doing fairly well. We're able to match this red curve decently well, and I'll leave it as a function of the reader to find the absolute values of w that you would need to actually match this curve even better. But what this shows us is simply that we have an ideal curve which represents our labels, but the functions that we will try to generally fit into it, the models, will be crude approximations of the same, which means that there will be some error involved. And how do we basically quantify that error is what we'll see next. So hopefully this makes sense why we have this sigmoid function defined very simply. Why are we using a parameter? It's so that we can actually reason about our inputs in a manner that our models can understand, and how they basically interact with each other, right? So I had promised you guys earlier that we'll have, let me just start this off really arbitrarily. That in addition to weights, we also have biases. So a bias is, put very simply, it's we generally think of um, weights as we this is the essential function of what a neural network does, right? So a linear layer, you would notice, which is one of the most fundamental blocks of how a neural network is built, is that we have these inputs x and these weights which are multiplied together, and then we add a bias. The bias's job is essentially to make sure that if there are labels and whatever that don't fit the data, we can actually use that to manipulate the entire data set as a whole, right? So yeah, that's putting it very, very crudely. Feel free to ask me if you want a more technical description. That's absolutely valid, right? The role of biases are actually pretty interesting, and in many cases you would find that there's a lot of research that goes into how to best quantify both the weights and the biases for a linear layer itself. And as we move forward, we will see even more complicated layers, which are more used by the industry in the real world. So for a moment, let's come back to our apple and banana example. So again, I'm going to be plotting the green values from the apple, which is red right here, and the green, which is the banana. So right here, we have our model with the weight and the bias that we can move around within the same function, right? Make sense? Um, so the idea again is that we want to figure out a way to handle to make this basically pass through both of these points, right? Um, and you would notice that it takes a little bit of doing to identify the particular set of weights and biases that will actually get us where we want. So as you can see, the bias was able to move the curve as a whole, right? Whereas the weight was what kind of manipulated how sharp it went from 0 to 1. And depending on the data set, that's going to be important. And as you can see, this is how by eye we were able to figure out a set of points which works decently well for just 2 data points. Um, so this follows our curve reasonably well, nothing too spectacular, but this is essentially the process of learning that we want to simulate within our machines, right? Um, so one question that I would ask you at this point is, when I made this blue model pass through my data points, what was the metric that I was actually looking at to make sure that it passes through the points properly? How do I ascertain that this model is any better than this model? Or what happens if I were to increase the bias? Yeah, how do I not only choose, but how do I know that this is a better model than this, for example? When it passes through none of the points. So feel free again to shout in the chat about why you might think that it might be the case. Specifically, I would encourage you to think about what it means for this model to pass through these 2 data points, right? Um, yeah, how would you quantify that? So I would probably want to say something along the lines of, currently this model as it is right here, it has a huge, huge error, right? So it's able to identify probably all my apples just fine, but it means that I will never be able to catch a single banana, right? Calculating how far the model value is from the real value, like a loss function, that is exactly correct, right? what this basically is trying to show is that the model itself needs to worry about a particular metric, right? That metric can be composed of different components, but that metric has to very accurately define what it is that we're trying to achieve, right? And in this case, intuitively, our metric was how far away the model is from our data points, right? And essentially, in more concrete terms, it means that this distance, the distance of the model from these data points, is what we're trying to minimize, right? So essentially, this is what we're going to try to simulate um, further on. Now, getting into this, we'll see that this is a bit more mathematical as we start getting into the weeds of things. So, guys, let me know if you want, a little bit of a break, get some tea, get some refreshments, so that we can come back to it in all prepared, and then we can tackle what our loss function means and how we actually go about the concept of learning. Also, in general, let me know when you would want a few minutes off. Uh, Depending on everyone's wishes, we can have a break from between 5 and 15 minutes. We can do multiple breaks to break down, the different logical segments that we have going on. And more than that, let's make sure that nobody is overwhelmed either. So, what do you say about a 10-minute break right now, and then we can reconvene so everyone can grab yourselves a coffee or whatever, and we can get right back into it, shall we? Does that sound good? Yep, cool. Let me put a 10-minute timer, and I'll see you guys in 10 minutes from now. Thank you. All right, so hopefully everyone is back. I hope you got yourself something to drink. So now we can, get started on the next real step. So before we dive right in, um, does anyone have any questions of what we've done so far, or even any real feedback in terms of if you think things are going too quickly, too slowly, however, I'm happy to take some of that. Okay, cool. Right pace sounds right about where I want to be. So cool. Let's do a little bit of a recap. Um, so we basically saw that when we have only two data points, it's fairly easy for us to understand what the models are doing and how we can encode different behavior within the model. And of course, I completely recommend you guys go through some of these notebooks yourself as well. It helps capture a lot more of what I'm talking about in a bit more sense because not only do you have the code, but you can actually do all of these manipulations by hand and see how it actually figures out. Um, right. Uh, so so far, I have basically shown you how we think of a very simple linear layer, essentially a linear model, and how we can use a parameter and a bias, a parameter in this case the weights and the biases, to fit our model, the blue line, onto our data set, which is the apples and the bananas. Now, of course, these are just two examples. In the real world, even as we go through this training, we'll see that not only are we restricted, not only are we, expected to work with hundreds and thousands of apples and bananas, but also how do you model different aspects of the training process. So this is done by something called learning, right? So learning by nudging is what we're calling it. So the idea essentially is that we have a metric that we call our loss or the error. Try to minimize that error, and we'll now see how we minimize that through learning. Uh, so let's first of all quantify what we meant by our error, right? We mean the error between our different labels. So one label is at 0, another label is at 1. So this is the banana. So we want to say that our uh, model, our prediction, has to, we will add up all the different, distances from every single label that we have. So in this case, we have the distance of the same parameters. Notice that W and B are in fact the same. So for every parameter, we want to calculate the distance between the model and the ideal label and a prediction value. And because we want things to be all positive or nice and positive, we'll square it up. Um, that way we can be guaranteed that there is no one you know uh, uh, symmetrical losses don't cancel each other out. We don't really want that. We want every single category, every single label to be identified properly. So we have two data points in here, x1 and x2, x1 and x2. And let's just code this up really quick, right? So as you see, the code looks very familiar to what our mathematical notation does, right? So we do 0 minus sigma of the apple WB. So the same WB that we have here, squared plus 1 minus for the same thing for the banana. Uh, and that's really cool, right? It means that we're now able to, figure out our loss surface even better. We now have a mathematical notion of what a loss really looks like. And the next thing that I want to talk about is how we actually, come up with our our model essentially. So far, we've loaded up our images. We've seen that the average numbers don't work out, and we've made our plots. So we've been able to intuitively fit our model. Uh, One really tricky thing that we would do, that I would actually leave as an exercise for for the readers, is try fitting the same model but with a couple of different additional data points, and you would suddenly see disaster breakout. By which I mean it will be very difficult to fit a single model over over a large data set that fits all the values properly. So what we want to do essentially is sum up the loss from every single data point that we have, right? And that we're interested in. So in this case, not only will our x1 and x2 be floating point numbers as we have right now, but those would become vectors and arrays, and so on. Cool. So let me also do this thing really quick, where I have a bunch of these sample a bunch of these weights and the biases. So let's say I go from 10 to 13. That's essentially where we played up and found is the sane spot, so to speak. So let me do this thing really quickly. So in my title, let me add W equals W2 equals $P. So what I'm really doing here is called string interpolation, which is basically another way of saying that add a title where you replace anything around this after a dollar, essentially in these brackets, can be arbitrary Julia code, and replace whatever is the output of this Julia code with a string that you put here. So that's essentially what I've done here. And what this means is that it allows us to visualize the changes in our weights and biases as I'm making them. So as you see, a very small difference in W and biases can mean a very large change in actually how the model responds. So the exercise that I'm expecting you guys to do is essentially add another data point and try fitting the model again. So we want to find out this ideal set of weights and biases essentially, right? And what we end up understanding is that there is no one particular value which satisfies our conditions. In fact, there is a whole family of weights and biases which works just fine. And that basically brings up the question, how do we know anything? How do we know if we're at the right place? And one way to do that is actually sample a very large swath of weights and biases, and then we sample a loss function over the entire um, search space essentially, and then pick out the one where the loss is the least. That's a very rudimentary way of doing it. It's very inefficient, but the fact is that it will actually give you the results. We want to do something much more intelligent though. And what we want to do is we want to figure out how to minimize these functions. And the way these functions are minimized mathematically is that we So we move around our sliders, we know what the weights and the biases do, yada yada. We have bigger models, more data. We always want more data. Um, and that's helpful. Right. So this is the tools notebook. I'm going to go over this really quickly because there isn't much code in here. I just want to make sure that people have the right notion of what we're trying to do, right? So in Julia, we saw that we messed around with our weights and biases. So loss with a weight and a bias. But essentially, what it really translates as is just a parameter to the function, right? So like if we have f, x, and w, so x is our input, w um, is our weight. We're able to send this to our sigmoid function, which gives us the output. Now, I could write a very similar g, x, w, b function, which, so in Julia, the way I represent, uh, the sigmoid function, which is Unicode character, I can use the inbuilt sigmoid function always. That's uh, you know, just up to me. But if not, we can always do this thing where we type out many of these Unicodes. So like sigma, uh, start with a backslash, type sigma, and then press. Oof, that did not work. So you need to do it a bit quicker than I did. Right. So you do backslash sigma, tab, you'll get you the sigma operator right there. So as you see, I can now also define a function which takes both a weight and a bias and is able to forward it to the sigmoid function just like before. So there is no effective difference between how Julia treats um, an x versus a w or a b. These are just arguments to functions. Um, when we try plotting, you would have seen these kinds of operators sprinkled all around. And apart from all the things that should make sense, the while limits and the labels and so on, this is just a shorthand for an anonymous function. So basically, anonymous functions is something that people might be familiar with from other programming languages, so like lambda functions and so on, which basically says that this takes one argument x and it's forwarding it to uh, f w comma uh, x. So in this case, the w is being picked up from here, right? Uh, and again, so this was a really high level overview of how functions are defined uh, within Julia. And apart from that, here's a bunch of exercises that I would really uh, appreciate it if people went through. These are very easy to do, but they also show the kinds of things that I'm trying to say in much more clear manner. Because again, you'll be dealing with the things with your own hands, which is always good. Um, so we saw how we are able to increase our model complexity. We were able to, get a very simple model fit. But as I said, add more data points and you'll find that that's no longer the case. So what gives, right? And one answer right there is that we need a more complicated model to be able to fit more complicated data. We saw that we could customize a model by adding a parameter, and doing so, we were able to fit the notebook. But moving on, we'll see that as we add more data, fitting a model is not trivial anymore. And we can't just keep adding parameters every single time, right? Because that will become very unwieldy.
Not to mention being significantly more difficult to train. Let me check this one. Right. Can someone make sure that they can hear me fine? Okay. Let me log back into the session. That helps.
Okay. Hopefully this. Um, Let me know if this improves. Cool. Sorry about that. And let's share the screen again, and we're good to go. Right. So we want to increase the model complexity, but it's very difficult to keep adding parameters every time we want to do that, right? Because I'm sure many of the folks here are already aware that machine learning itself is treated as a very computationally expensive field in general. Um, what we want to do, what we want to do is actually make sure that we're able to get the most out of our models in terms of the complexity and the performance. But we have to match it in terms of both making sure that the models are complex enough to fit our data sets well enough to get the generalizability that we are looking for. We don't really want models that can work well on a training set but fail completely if they see new data, right? So model complexity is where we're at. So let's look at the process of learning. And as I stipulated before, we want to be able to minimize a loss function, right? So our loss function in this case is just this thing right here. So the real output minus our predicted output squared for every single one of these labels. So let me plot this loss function right here, right? Really quickly. For very particular values, so you would see that this is taking it for just one particular x and f, uh, sorry, x and y. So y is our label and x is our input. And if I were to plot this, it shows me that it looks sort of like a hill, right? This is how we interpret our loss function. And the idea is that we want to be somewhere at where it is at the minimum, right? Um, so a few things that make it easier for us in this particular case is that we have a fairly simple data set to deal with, right? And what we're also assuming is that our loss function itself is very smooth and continuous, which means that we can again differentiate it, and that will become interesting because uh, knowing that we are at any given particular point in this you know in this hill here, how do we know where to go? How do we know how to change our weights and biases to, in fact, get to the minimum point and, in fact, guarantee that we will make it to our minimum point every single time? So this is somewhat of a question for the chat. I'm opening it up to everyone. The derivative, right? So what we are interested in right now is that we have our data point anywhere along this line, and we want to make sure that we are able to take our uh, loss function with the different values of the w's and the b's to make sure that our loss is in fact at the minimum point. So the derivative will do exactly that. What it will do is it will give us a measure of the direction in which we're supposed to move. So how is it defined? It's essentially the slope of the tangent from any given point. And if that slope is negative, we know. So you can imagine if the data point is here, the tangent would go somewhat like this, right? And if the slope is negative, we know that we can move along to the right, and that's where we want to end up. Whereas if we are somewhere here, for example, and the slope is positive, we know that if we move to the left, we'll actually make it back into our little area, which is the bottom of the hill. So this is how we basically calculate our uh, the direction in which we're supposed to move. Now, that's all fine and good, but how do we actually calculate the derivative and our gradients? One way that people might be familiar with from, again, high school is this little approximation, right? So you calculate the slope of this line, essentially, and you make the step size very, very small. So this is one way to calculate derivatives. Of course, this is by no means the only one or the best one and the most efficient one. This is a numerical gradient, and of course, as before, we have a W, and this time we have a loss function. Note that we are in fact using a function that we have written ourselves, a derivative of at any given point uh, based on our weights is given by f x plus h minus f of x upon h, and our h in this case is small. And another thing that I'm doing in this plot here, let me go through the code so it's more obvious what I'm trying to do. So I'm going to be plotting my loss from -2 to 1. That's what this line says. And I'm going to be labeling it L1. That's right here. It's in the legend. So I'm going to be picking out my initial points, x naught and y naught. So my y naught is just going to be the prediction that the model thinks it is right now. So my x naught is just the weight. My y naught is the prediction at that point. Next, I'm going to add the little ball that I'm interested in. So this will plot this ball right where my x and y are. Then I'm going to calculate the derivative, and I'm going to be using this formula right here to calculate my derivative. This will give me the derivative with respect to w. Um, and next, I'm going to be plotting this straight line, right? Um, so this will be a tangent touching the function only at this point in here. So by using the simple formula of the line y equals mx plus c. So we have our intercepts, we have a slope. So this is the slope, and we have x minus x naught, which is our origin point. Make sense? So we have our derivative line, we have the scatter point, the point itself, and the plot of the entire loss function. After that, this is just a matter of making sure that we plot only from some certain limits to certain limits, and we have a nice little visual representation of what the weight is and what the derivative is at that point. Does that make sense? Cool. Um, so again, as before, our job is going to be to find the minimum loss. Actually, let me do this really quick. Let me also populate my title with the loss. So this way we have a clear-cut idea of. Let me also make it a little smaller so it all fits in the same little area that we have here. We can keep track of things easier that way. Actually, this place. It's nice to be neutral. All right. So we see that a derivative is negative 0.39 and our losses are 0.34 at some weight. So from earlier, we know that when our when our derivative, excuse me, is negative, we can move in the right direction. So we can increase our weight, right? So let me do that really quickly. And as you see, as I have increased my weight, I have moved to a position where my loss is my derivative is still negative, mind you, but my loss is significantly lower, right? And as I optimize it, I should be able to get to a point where it is even lower. And as you see, my derivative is now close to zero. Um, One thing that we know now is that when our loss is basically optimal, our derivatives should be close to zero, right? And that makes sense because you don't really have to move either left or right uh, when you're at your destination. You just stay there, um, and that makes a lot of sense. So congratulations, everyone! You have trained your first very rudimentary neural network almost automatically. But now what we want to do is we want to codify this entire process, right? And how do we do that? We do that by this really beautiful algorithm called gradient descent. Um, Now, right before we jump into gradient descent, uh, does anyone have questions? I'm happy to take up any questions, any commentary, so that we can all get the right abstractions in mind as we move from here. As always, feel free to put things in the chat. What software are you using for the notebook and code? Uh, Good questions all around. So software, I'm just using Julia, and the notebook environment that I'm working on is called Pluto.jl. I spoke about that a little bit earlier. So Pluto, you can think of as a substitute for Jupyter, if you would have heard of it. So let me put in the chat. It's fairly simple to reason about, and it's completely reactive style, which means that rather than having some weird state like Jupyter almost ends up having, anytime you're working with large notebooks, you'll see I have had next to no issues running it on my little laptop here without trouble, um, especially with any bugs in the software. Are these files thought to be used in a Pluto notebook or run on VS Code? So that's a very good question, and the answer is kind of both. Um, so I have a Pluto session run separately from this terminal window right here, and it is doing much of the heavy lifting. But in general, all of this code is being run inside the Pluto environment. And anytime I want to refer to code that I run specifically in in VS Code. I'm usually in the VS Code screen. Does that help? Cool. So right before we jump into gradient descent, let me basically do like a 2-minute summary of what it was that we just achieved. Right? We understood that we have certain data or input data that we're trying to fit, and we have some parameters that we can actually think of as dials that we tweak, right? So our weights and biases. Um, and we use these in a very simple you know, linear layer, a linear model, and we calculate the derivative of a loss function, which tells us how far away we are from where we need to be, and we calculate this derivative, and this derivative then tells us the direction and the amount by which we're supposed to move. So the sign tells us the direction, and the value tells us the amount by which we're expected to move in that direction. To update our parameters of weights by moving it in said direction to minimize our loss, to be able to fit our data points best. So if I were to go back in here, I see that um, weight of 0.51 and a bias essentially of 0 works fairly well to fit uh, this particular data point. So if I wanted to get a model which will fit this particular data point really, really well, I would end up with something like this. So a weight of 0.51 would work swimmingly. So now we have the basic structure of how this learning program works. And then I promised you that this is an iterative method. So I promised you how do we actually calculate this thing, right? And I'll basically talk about this concept of gradient descent. So even if the tangent line is a good approximation of where that function is in that point, we want to be able to measure exactly how much and how far away we are, and we're doing that through a different gradients or partial, so to speak. Um, so at each step, what we end up doing is we calculate this derivative, we update our our weights, and then we do this whole process all over again. And hopefully, by the end of it, we reach a minimum loss. So we start at some. So let's go through what is expected of us really quick, right? So we start with an initial guess W naught for W. At each step, we calculate the derivative. So L1 prime, the prime is how you know it's taking the first derivative. So at the current value Wn, using the function that you created above, modify the value of W by a small multiple. For example, so eta is 0.01. So we multiply the value of the gradient with 0.01, and then we multiply the value of the gradient with 0.01, and then we update our W right here. So basically our update step basically becomes Wn plus 1 is Wn minus eta of the gradient. Cool. Does that sound good to everyone? Cool. So our job now is to basically make this into code, right? And this is where we see a few tricks of of Julia. Now, I'm sure many of you are familiar with how a bunch of Julia's internals already work, but one thing that Julia prides itself on is uh, having really fast, being a fast language and having fast semantics, especially in terms of how do you express your problem best, right? So one thing that the one first way we're going to express our gradient descent function is just as some arbitrary function f, and we will now basically try to do this descent over a range of different w's, essentially of different parameters. Um, Again, the x and y is what we had selected earlier. So this is a completely fictitious example. This does not use our apples or our bananas, but the idea is that we're able to see what is happening. Uh, so we calculate our derivative like earlier, and we basically go from 1 to 2000. We calculate a derivative, uh, and we update our weight or W by this formula right here. So we multiply the derivative by 0.01. We had our eta, so this is usually called the learning rate, and then we update our weight, and then we calculate the derivative again, and we do that over and over and over again. So this is really cool, but notice a few limitations right here, right? First is that how will I ever know that my function has already reached its minimum? Um, First answer is that I just hard code the number of steps that it's supposed to take. But frankly, that is not good, right? Because in certain cases it may not be enough, and in others we are probably already at a minimum and we're just wasting CPU cycles. And in an already computationally expensive field, that's absolutely frowned upon. So this is one way of doing it, not very ideal. So what we want to do is we want to have somewhat of a tolerance built into our network. One thing that we spoke of earlier was that there is no way that every single data point in our model will be fit absolutely perfectly, right? Which means that even if a loss of absolute zero is possible, and in many cases it might be, we generally do not want a model that can take the loss to its absolute zero, because of the simple reason that that means that the model would have quote unquote overfit, which means that anytime I give it, it may be too, following the curve too tightly, which means that anytime I give it a data point which does not exactly meet the specifications from the data set that we trained it on, the model will have no idea what to do with it and will get really, really poor results. So based on that, our idea is that we always want a more general model, a generalizable model, rather than one that has the minimum loss. And this is where we, come into the concept of breaking down a data set into, uh, training data sets, validation sets, and test sets. And one of the really key metrics that we're looking at when we do that is that we want to understand the tolerances in which we are okay for the results to be, right? So in this case, there is no data set, so to speak. We just have one data point. Um, but we want to have some amount of tolerance built into the network so that when we exceed that tolerance or basically have a loss lower than that tolerance, we're able to say, okay, we call this trained, let's call this converged, let's see how we're actually doing. So if you notice, the loop here is slightly different. No longer are we restricted in the number of steps that we take, but we let the model train as much as it wants to, and we stop absolutely whenever the step itself is very small, which means that we are no longer making very drastic progress. Is when we stop. the good, the benefit of doing that is that when our gradients are small, we know already that we will be calculating many more of them, because of the fact that the step size is going to become even smaller when multiplied uh, with the learning rate. But it also means that we will stop at some point. So there's definite stopping condition built into the model, which is going to be hopefully much earlier than any hard-coded number of steps that we ever give it, right? So that's the intuition behind it, you can say. So in this version of gradient descent, what I have done is I have also stored the value of the weight and the loss at that point, and I'm now simply plotting it. So does that sort of make sense about how gradient descent functions really? So feel free to shout any questions. Although this is implementation for a real valued function, and that's very true. That's an excellent point. Uh, you will, of course, end up with situations where that might not be true. And uh, how does gradient descent will know when to get out? That is an excellent question as well. Uh, so although this is an implementation for a real valued function, that may not always be true. Let me go step by step. Um, and in cases where it's not, we generally try to encode that information within the structure of our model itself. Calculating gradients is a very general approach. It doesn't exactly really need every function to have real uh, real value outputs like here. But in cases where we have, for example, rational numbers or complex numbers in play, it is absolutely correct for us to use those functions as well. So this is a simplification for sure. But the idea is to get the intuition going. But yeah, that's absolutely right. We can definitely apply machine learning to non-real valued functions just as well. In case where there are two lows in a data set, so basically two minima, uh, how does gradient descent algorithm know that we will actually reach uh, where we want to go? And the question is that it wouldn't, right? In many cases, so for example, let me plot sine minus 5 to 5. So in this case, assume that this is the data set that we're interested in, right? Um, Let me actually do it till 7 or so. All right. So in this case, we see that our loss function, if this is the loss function, we see that there are two minima essentially, right? Here and here. Now they may not be equivalent, but the problem that we would face with gradient descent is that if we start our function or wait somewhere here, we might reach here, but we will never go up the loss function. Or if we're here, or if we're here somewhere, we would come here, but we will never know that this even existed. And in practice, you can completely and correctly assume that there will be multiple such points. So these are called saddle points, where you will get multiple uh, such points strewn across your loss function and your loss surface, uh, where your structural loss will not be able to identify that there is benefit to actually exploring further. Um, So for that, there are other alternatives to how training processes work. So you probably wouldn't want simple gradient descent there. You would probably want more complicated optimization routines, which are more interested in global sensitivity rather than just the local derivatives. Or you may want to look at much more elaborate optimization routines. So this is not something that is uh, you know scarce at all. There's a lot of literature around how do you deal with these saddle points and multiple local minima and finding the absolute exact ones. And a lot of them has to do with searching larger and larger swaths of our loss surface before and getting candidates essentially. So like candidate starting points where we would have the best chance of missing out on local minima and going to the global. So that's an absolute you know field of study. It's something that we actually might actually see later in the course as well. So those were good questions. Let me know if there's more, and we can take those up. Um, all right. So currently, through this, we have an exercise that we can probably work our way through, and it's fairly simple. We want to use these things that we've learned so far, and we want to fill in or blanks here. So let me do this really quickly. It's been an hour-ish. Why don't I give you guys a 5-minute break, and why don't you do this exercise, and then we can uh, huddle up and do a quick review, and then probably go over to learning with proper neural networks. Does that sound good? What would people prefer? How long a break would you want? You can do 5, 10, 15. I guess we should cap it at 15. We would need the time. 10 minutes. All right. 10 minutes sounds good. 10 minutes it is. So let me do a 10-minute timer, and I'll see you guys in 10 minutes time. Thank you. All right. Hopefully everyone is back. Uh, so first of all, let me know if you guys were able to follow along, and if you have any questions or doubts so far, I'd be happy to clear them up. Be they about the language, the packages, the code, the implementation, the logic, however. As always, feel free. Sorry, to shout in the chat or just unmute yourself. However, seeing none, we can probably continue. Gradient descent functions in which packages is a good question. So for this particular training, we have defined it ourselves. So as you can see right here, we have the gradient descent function that does the the most basic form of gradient descent right here. So you have different kinds of gradient descent actually. So one of the other ones would be a stochastic gradient descent. So it actually does sample the data points differently so that you don't get stuck in local optima. It was an earlier question, and that was a very cute transition to SGD as well. So yeah, any other questions so far? We will probably want to work on uh, VS Code as well in a little bit though. Like let me make sure that we have all the things in place. So as promised, I promised you guys that we would do one of the exercises together, and let's share some notes, shall we? So I expect folks to be, able to shout out the answers in the chat or however, um, for all of uh, you know these fill in the blanks. Oh, sorry, didn't mean to do that. Uh, these questions. So, what do you think? What do folks think? How do you fill in A and B? Uh, the hint that I can give you for it is that notice in the definition of derivative, we defined it somewhat like f x plus h minus f of x divided by h. And in both cases, I want to note that actually let me use w, right? Because just to be consistent. In both cases, we wanted to use multiple different kinds of parameters, right? But here we were calculating it based on just one of them. So this is how we defined derivative x w and h. So you can imagine x being the first argument to both of these, right? So this is how we defined a derivative function, essentially. And the right answer for that is basically that we can think of the derivative as just the 1D version of the gradient. Remember that we do gradient descent. We are interested in the gradients of all the parameters, right? And those parameters can be higher ordered as well. So one thing that is different between a gradient and derivative is that the derivative is almost by definition always going to be looking at just one axis of it. whereas everything else will be held constant, whereas a gradient would in fact use the partials for every parameter. We can visualize the sea as a hill. So what do folks think that is? So your options are gradient, loss function, derivative, gradient descent, and learning. So I hope you guys remember we called this our hill essentially. So what is this blue curve representing here? Loss function. Yep, that's right. So we can visualize the loss function as a hill. In most cases, what we would see is that it's not so easy to plot it. Not only because you would have a significantly more complicated loss surface, but in fact, notice I called it a surface. It might be higher dimensional as well. Uh, but yeah, definitely it's a loss function. Oops, didn't mean to go quite that far. In the explanation above, so what we spoke about earlier, uh, rolling downhill. So the process by which we got our ball from here to here means traveling along the what? So what is that rolling downhill process, the iterative process called? And what is it traveling along really? So the, to clarify things a little bit, it means this iterative process, and by traveling along, it means how does it know which direction and how far to go in that direction, so to speak. Gradient descent is the right answer for D. Yep. And how do you know in what direction and stuff to go to in this process? Derivative is close. So yeah, that's right. We move along the gradient. So the derivative is just one 1D version of a gradient essentially, as we saw earlier. So moving along the gradient is exactly the right answer. To quantify the correctness of a model, how do we quantify the correctness of a model? Essentially, we use a what? So this would be the metric that we use to describe how far away we are um, from our actual answer, right? We use a loss function, that's about right. So when a program can minimize a dash on its own, we say it is, what is it doing? When a function can minimize a loss function on its own, when a program can minimize a loss function on its own, we know what is this process of minimizing the loss function called. Loss function learning, yeah, it's learning, that's right. Uh, cool. So that was really cool. We were able to get through some of this. Um, all right. This was really helpful. We did this notebook called What is Learning, right? So we're here. Oops, I have solutions. That wouldn't be helpful. So minimizing functions is next. So this is a tools notebook. I would generally, encourage people to, look at some of the tools notebooks yourselves, purely because it's easier to, understand syntax by actually playing around with it, as I said before. And a lot of it is, in fact, similar to what we have seen earlier as well. So it's good to get some intuition around what it is that we're trying to do. So minimizing functions, we know how we minimize functions now. We know that we have to write our gradient descent essentially. So there are a few more exercises that we can probably do. Um, and one of them might just be minimization by gradient descent. So when our derivative is positive, um, it means that uh, what direction are we supposed to go if our gradient, if our slope is essentially positive? Um, it means that if we move from left to right, our loss function is essentially increasing, right? And that's the opposite of what we want. So uh, if our derivative is positive, which direction should we move in to minimize our loss? So that's an open question for, yep, left is right. And the opposite is true when it's negative, right? So when it's negative, we know that we can move to the right. Um, so we can use this information to basically, yeah, to inform our update step essentially. So yada yada, we'll implement gradient descent. So this is somewhat similar to how you guys would interpret these results, right? But rather than uh, having them just here, you would actually have to code them, which is pretty interesting, especially for someone who's fairly new to Julia. You would find how you can represent functions, you can represent different um, properties of functions using Julia, and that's it's pretty cool. So the next really big topic that we have is functions of two variables and the derivatives, and this jumps back slightly to how we had structured our problem earlier. So the difference between a gradient and a derivative in some ways, right? Um, so we call the derivative the 1D version of the gradient. But one thing that we also have to understand is that in machine learning, we accumulate the gradient over multiple functions, right? So we saw earlier that our sigma of x, w, and b looked sort of like 1 divided by exp of negative w times x plus b, and that's how we define the function, right? So as you can see here, when we update w, there's multiple functions that we're actually accumulating the gradient from, right? So one of them is multiplying it by x, another is adding the bias to it, so the gradient that it accumulates there, then negative, um, exponentiating it, and then inversion. So this is a number of different functions that it has gone through, right? And the trick here is to understand that every single one of these functions is just a function in Julia. There is no difference between how a machine learning model works versus how any other function works. So when we do our training process, we have to accumulate all of these gradients for every different function that we see throughout the process of a forward pass, as it's called. So normally how it is done in traditional packages is that we would have a container called a Wenger tape or something like that, which is simply put in array which records every single operation and the state at any necessary state that it needs to in fact calculate the gradient back when the function has to go back to get the gradient just right to update. And this is the loop that we're interested in. But in Julia, we do things a bit different. we say every function is just a function. So you don't really need special types or anything. The code itself gives you enough information to reason about what the gradient should be by the same chain rule that you would have learned in college in school. So the chain rule is essentially how we calculate our derivatives, and the chain rule, the opposite of the chain rule is exactly how we accumulate our gradients. So the opposite direction essentially. So let me do this really quick. So let me ask for the gradient of my sigma at say x1 uh, w and b. So w and b. Actually, let me do it a little bit cleaner. Is everyone able to see my terminal just quickly? Cool. So, oops, I made a mistake. I shouldn't have pressed enter. Yeah, that was fine. To w comma b. So 1.5 is essentially w. I'm assigning b 0.6, and I'm saying my sigma at some x, w, and b is supposed, and I'm saying it's an arbitrary label, right? So I'm saying basically calculate the gradient of w and b at these values with this loss function. So essentially I'm saying how close or what is the gradient when I want to calculate w, a banana for this w and b. And as you can see, I get my you know gradients right back. And I can use these gradients to update my W and B using a learning rate. So my eta be 0.01. So I would say, okay, let me make my uh, oof, that was unhelpful. So if I have this, copy, paste, and voila, you see that my gradients are now much lower. If I were to use these values directly, so let's say I assign 1.5 and my p can be 0.6 minus this thing, and now I calculate sigma 1 w and b. I find that it's very close to 0. Wait, that's not right. It should be very close to 1. Oh, it's an iterative process as well, remember. So like you have to do it over and over again. You have to multiply it by 0.01 for a start. And this. So now you have your new weights. So now you can calculate sigma. And as you see, it's now moved from its earlier. What was it? So it was 1.5.6, right? So as you can see, it's actually grown lesser. And if we keep doing it, we'll find that we actually eventually converge on the right levels that we want to be at. So we saw how we can find our minimum. I would encourage you guys to check out the Plotly backend for plots. So using plots, and you can just do that by calling Plotly. And after that, any plot that you do will be using the Plotly backend. I must have some open already, so it might not do the exact right thing. But the first one thing that you have to, you learn with Julia really quickly is that the first operation is almost always a bit painful, and the reason for that is that so right here you have the Plotly backend. Um, the first operation is a bit painful because it does all the compilation, beforehand. The second one is going to be really fast, right? So like you have to compile it only once. So like if I had to do the same thing for cosine and I plot it on the same window, I see that it's much faster. And if I you know, keep plotting, it'll give me the exact numbers as I want. So this is and if you want to switch to the GR backend, the function is just to call GR, and anything else that you do from there on, you'll be using the GR backend. So that's really helpful, just to know where we are and what we're doing. Now, why I suggested using the Plotly backend is because as you read through the notebooks, you would find mentions of 3D graphs. And one thing that we haven't shown here, but is in fact very useful, is this is just one surface, right? So this is just one slice of a surface essentially. Whereas it's an entire surface that we are interested in. Notice that we did have an entire matrix of loss function of loss values, right, over a vast array of W's and B's. So our loss surfaces are actually three-dimensional, and this way we can actually plot three-dimensional figures much more cleanly compared to GR, and that way we can visualize and manipulate these graphs to understand how our loss surfaces are in fact structured and how we can best make them work for us essentially. So you would also find cases where you have to write partials. Partials are essentially the derivatives for a particular uh, you parameter. So a partial for b would only manipulate b in the derivative formula, keeping everything else constant. And yep, same for partial w, and so on. So these are the kinds of things that you would find. Very simple, and you would also find this particular exercise. This is one of the ones that I think is really interesting, and we can definitely go through it together as well. And this is simply doing gradient descent in 2 dimensions. And as you would see that we would also want to do gradient descent in 2 dimensions because we want to be able to figure out how exactly we're supposed to move on the lost surface. So it's not just in one direction, right? We can go in multiple directions. So especially for people who have done optimization courses before, this would be very, very familiar. Moving around surfaces in in many dimensions. So multivariate calculus people would be very enthusiastic about this. I hope. I feel. Uh, cool. With this, let us now formally jump into the world of neural networks. What you saw initially, the sigmoid function, the linear function, was a very simplified version of what a linear layer looks like, right? So a layer basically has a bunch of these components. It has parameters. It has a transform, and then typically it will also have a bias and an activation. So a bias would be added to make sure that you can manipulate the function left or right as needed. The transform is just the transform that the function is actually applying. The parameters are the things that will actually control how they would react to different inputs. And an activation is a smooth function which will you know try to ascertain which parts of the neuron are actually activated or the neural network are actually activated and suppress others. So that way, if there is significantly more discrepancy between which neurons are firing and which aren't, and by firing, I just mean they're outputting a very high value versus a somewhat of like a zero value, you can imagine that one neuron can stand for saying, oh, this is an apple, and another one can be, oh, this is a banana neuron. So if the apple neuron is at 99% and the banana neuron is at 0.01, you know that it's an apple, right? Straight up. So far we've been using the sigmoid function. That's a very, very simplified neural network. But what happens if we have many, many features, right? We have many, many features that we're interested in and features that we want to discover. Now, that simple network will no longer suffice, and we need something which can do a lot more complicated things for us all of a sudden. Um, and rather than having single values, single floats, we'll now have vectors and arrays to deal with. So how do we do that? And one simple, very simple concept of a neural network comes about, or a neuron comes about. So let me go back. So learning with a single neuron, right? So like we have, in this case, we're showing a two input and one output neuron. So this is the same. This is the only neuron that we have so far. So basically, it takes in two inputs. It does the transform that we saw earlier, and then it outputs the value that it thinks it is. Um, but rather than doing it on just one data point, we now want to do it on a swath of data. So what does the roadmap effectively look like now? Let's see. So the goal is that our neuron will take a single point on the two-dimensional plane, so i.e. there will be two inputs. Um, as input and should return a single output that it classifies as an apple or a banana. To do so, it must learn the correct values of the parameters w and b. And for this learning to take place, we'll need the labels and so on. These labels will in turn allow us to create a loss function, which will allow our algorithm to learn and determine if given a choice of parameters does a good or a bad job at classifying our fruits. So what do we have left to do, right? So we saw that we took in one apple and one banana each, but now we will change the game a little bit. We'll now load many, many apples and many, many bananas. We'll create a sequence of labels that we need. We'll define the loss function and we'll implement the same gradient descent routine. Now, we'll basically bring all of this together in one go, right? And it will become a lot more obvious very soon. So there's a different notebook that we'll jump into, and you will notice that the repository, the GitHub repository that you downloaded either as a clone or as a zip file, also has a data folder, and that data folder actually has these data frames in it. We're using the CSV and the data frames package from Julia data ecosystem. Now, one thing to note here is how well the ecosystem actually plays together. So even though we're doing machine learning, we're able to use the default CSV readers and data frames, and we'll see how we can use the same data frames to actually throughout the training process as well. So this is the part that generative programming gives you, that you're able to use different parts for without having to rewrite everything to suit one particular framework. and any operations that have to happen within themselves can also be done by just normal Julia. There is no need to have glue languages built in. So when I read this data frame, I see that um, I have a bunch of these heights and these widths. Not so interesting. Maybe we can use them when we're trying to do something differently. And then we have the final mean red, green, and blue values. So every one of these rows represents a single banana in this case, right? And says that there's a mean of point. Oh, maybe this is an apple. This is an apple, my bad. Uh, like all the uh, apples, every single one thing them is basically an apple. So all the reds, the greens, and the blues. One thing that we would we earlier saw the concept of feature engineering and feature selection when we saw that we could not in fact use the red values to distinguish between our apples and bananas for the pure reason that our data set actually does not favor redness as a distinguishing factor. Um, Another thing that we would see is that we would want to normalize all of our values, right? So luckily, uh, you know, this is something that we wouldn't have to do very heavily here, but it involves all the steps that we have to do to pre-process the data so that it can be ingested by our ML training. Um, so yeah, that's about all I have to say for that. Um, So this is the apples. So if I had to pick out uh, just the red column out of it, I would do apples colon red. So this will pick out just the red, and as you can see here they are. Similarly for any other, so if I wanted to do it for bananas and I wanted the green column, that's all I really have to do, and voila. Next thing I would want is I'll use only so my task here defined previously as I want to create a two input neural network, right? So I'm going to choose kind of arbitrarily that I want my features to be the red and the green value. Now, we spoke extensively about the importance of feature engineering and feature selection. One thing to note here is that uh, in many cases, when we have a very very large number of features, how do we choose features then? And the answer to that is that we have many different metrics that we would use, effectively all trying to figure out what kinds of features would describe the most variance in the data set, because those features would be the ones that would distinguish between the different labels the best, because labels are supposed to be separated, right? So the variance will give us that. Um, in this case, we're choosing the reds and the greens, almost uh, arbitrarily, but this would formulate essentially our what do you call it? The access, the inputs, and similarly, we would have the Ys. So the Ys are basically zeros for all apples and ones for all bananas. So we fill an array of uh, array with zeros of size of all the apples. So right there, and we have the same thing for the bananas, but we have one as our label. So you will notice right here that one thing that it is not doing is we're not mixing our data set quite nicely, right? So in a typical machine learning training pipeline, you would in fact be expected to have your data set shuffled. Um, just for keeping it simple, we're going to be keeping it separated, but in general, this is a good idea to note that we would, in fact, expect folks to make sure that the data set is completely shuffled so as to not introduce unnecessary bias while training. Um, so after that, we just want to plot our data set in 2 dimensions, right? So like we're now able to say that, let's see what our data set looks like. And lo and behold, we see that there is really good separation. In fact, all of our apples are all right here, and all of our bananas are right here. And that bodes really well, right? Because that's exactly what we wanted our feature engineering to accomplish. We wanted to get the features that would be separated well enough for our neural networks to learn so that we can generalize best. Now, you would notice that in this area, it's a bit more difficult for our ML routines to actually understand how to pick between one or the other, purely because we have no information about you know, what the transition period is, which is exactly where we would utilize the whole concept of generalizability, that we do not want to actually overfit our data set in any way. So currently, this is going to be doing a linear separation, right? Rather than doing it on multiple dimensions. So rather than doing it on 2 or 3 or 4, however many dimensions, you will probably try to fit a linear model first. And the reason for that is, again, we're just trying to understand the concepts here. Um, so uh, please come up with any questions that you guys might have. I'm happy to take those up at this point. Any confusions, any questions, questions about where we're going, if things make sense. If they don't, I'm happy to take them up right now. All right, seeing none, are why does the distributions of the bananas look like it has some weird structure? Um, that's just an artifact of how you know, bananas. That's interesting. Like it's just an artifact of the mean values, right? There's nothing um quite important in that particular structure, I would say. It follows a linear path, which is somewhat helpful, but more than that, it's pretty benign. Unless we're looking at different features that we want to glean from there, it's uh, yeah, there's very little to note in that. No, of course not. Like it's always good to ask these things. Um, what is the high-level concept of neurons? Is it similar to represent data set and matrices? So let me put this in simpler terms maybe. So when we try to have uh, for example, okay, let's look at this, right? So we have a neuron here, which is it takes 2 inputs and it returns 1 output. So you can imagine that the things that connects these inputs to the neuron itself, right, are these weights. Effectively, this is x1, this is x2. So you have w1 x1 plus w2 x2, and then you would add a bias over it. So that bias will there will be a bias for every single one of these weight parameters. So you have b1 and b2, and beyond that, you would have an activation function, right? So you have multiple inputs and 1 output. Um, but you will not always be so lucky to actually be able to have just one output or have data set which is very very simple, right? So you might want to look at things like, what if you have um, 5 inputs, and then maybe this is the structure that you're looking at, right? So in this case, you have not only many many inputs, but you have a much more complicated structure of the neural network itself, right? So these are layers that are stacked one on top of each other. So why we would want to do that, why we want to go deeper and deeper, essentially one thing that I can tell you straight off the bat is that a deeper neural network is only ever useful when you want to have significantly more capacity, so to speak, to learn more complicated data sets. But in theory, um, every one of these more deep networks can be very concretely defined as just one layer networks themselves, as just being transforms over a one layer network. Um, why you would want to do that is because you would have multiple connection points at every single one of these. So for example, you can imagine if you have multiple fruits, for example, or different labels, essentially you would probably want to control where exactly those things are going to fire, right? So for example, if this layer is very quickly this neuron essentially is able to very quickly determine that there is no chance that this input data set, so you have inputs coming in from one, two, three, four, five different places, right? It determines that there is no way that it can ever be a banana. It will always be a zero, right? Which means that if we propagate that information very clearly throughout the neural network, which means that you don't need quite a wide enough network to actually codify the same amount of structure. So the high level concept of neuron is essentially that it will take in inputs from multiple sources, and if trained right, if trained just right, its parameters would be at such a point that they would only ever fire, so to speak, when they detect a particular kind of signal. So the signal can be a linear transform over the input values with the parameters themselves. Does that make sense? Yeah, yeah. Every single one of them can be thought of to define these connections. Now, of course, as I alluded to before, there is absolutely no need for us to go incredibly deep because the same thing that we're going to be achieving by going that, we can also go by having that in the first place, having the thing trained properly in the first place. So, but good question, thank you. um, at this point I think what we want to do is we want to do a little bit of learning with just a model with one neuron, and then we want to see how we do it with flux. So this will be the point where I introduce to you the Flux, machine learning framework essentially. So before that, would folks want a tiny break so that we can get ourselves something to drink, you know, take a little step or two to make sure that we have all the concepts in place, and we can even revisit anything that needs to be revisited. Happy to do that. Does that sound like a good idea? 10 minutes. Yep. All right. Let me grab a 10-minute timer. Okay. I'll see you guys in 10 minutes then. Thanks. All right. Is everyone back? Ooh. All right. Seems like folks are back, and we can jump into the last section essentially that we have for today, and it's basically bringing all of this together um, in terms of what we have learned as well as putting all of it into actual practice. Um, One thing we would see through here is that we will be using the Flux machine learning ecosystem. So you know this is just the GitHub page. This is the actual website that people would effectively see as their first jump into Flux. So you'll have tutorials. Soon you'll have more of those things about the ecosystem, the documentation, uh, blog, things that we have worked on and continue to work on. Um, so let's talk about Flux and the Flux ML ecosystem, shall we? So you can see that all of the um, what's it called? The development happens um, in the open on GitHub, and we try to be one of having both ease of use, elegant code, as well as fast performance, because that's what users expect, and that's the idea behind Flux. We want to be, you know, we want to understand how we use this ecosystem to actually solve our problems now. Um, all right, so let's jump right into it. Hopefully, people can see um, my VS Code screen. Do shout at me if you can't, but um, if things seem fine, we should be able to jump right in. So the first thing that we would do is we would load in all of our packages. Um, and I should have precompiled all of these things beforehand. That would have made it much, much faster. But c'est la vie. Uh, for now, we should be able to, load our apples and bananas in the same data frame that we saw earlier. But rather than stopping our story at plotting them, we'll see how those plots actually become useful, and we'll see how we end up training um, our our model. So as before, we have our apples and bananas. As before, we have our features, and as before, we have concatenated them. So now we have both our features and our labels handy. So how do we get going? Simple, just do using Flux. Luckily, I had that loaded, and now we will build the same neuron that we built earlier. Excuse me, not this one. 2 comma 1, that's the one that we're interested in. Yeah, this one. Um, so 2 inputs and 1 output, and that's what we'll define with Flux. So Flux has this really handy dandy dense function. So this essentially does the same thing as this neuron, this 2 input, 1 output dense layer, and exposes that for us in very digestible format. So you want to create a two input and one output model that will represent a neural network. And cool, we have done that. We can also add in things like our activation functions, or and these activation functions can be really whatever you want, right? We don't really restrict users from even rolling out their own layers. So, for example, if I wanted to write my linear layer, I would write it somewhat like this in Flux. Um, Sigma equals identity. And you would notice that this is very, very similar to how we dealt with things earlier. So sigma dot w times x dot plus cool. Um, and both of them are absolutely completely equivalent. So what I'm trying to emphasize here is that when we expose things written in Flux, we actually expect the users to have specialized formulations that they would want to do, be it with not just the transforms, i.e. the layers, but also with things like the optimizers, the training routines, however you guys want it, right? So we support a large array of the kinds of problems that we solve, right from you traditional deep learning to three-dimensional deep learning, as well as things like differentiable programming. So scientific machine learning, use of different accelerators like uh, GPUs and TPUs and so on, and that's all very, very exciting. It's a bit more about Flux itself. For the task at hand, we should be able to just have a two input, one output layer right there. And as earlier, we can also check out what our weights look like, right? So our weights are essentially this one particular array. So it's just a row because that's what we asked it to do. Two inputs and one output. So if we had, let's say ran 2 comma 1, right? And we can pass that along to our layer. And as you see, we will get uh, one output for two inputs. So that's essentially what we wanted to do, right? Let's use Flux to build our neuron with two inputs and one output. There you go. Now we can also, look into what the bias is. So the bias is just one element because it needs to be just one element in this case. We're just interested in one output, excuse me. Um, and let's see how we can call for all the parameters that a layer holds, right? So we can do flux dot params, and we can just pass in our layer. And as you see, this returns this params object, but what it contains within it are the weights from earlier. Notice this 0.5900, 0.5900, and the bias. So this way, if we have a very large model, so think of a ResNet, which can have like 50, 150 layers of a transformer, which is so much, these massive models that keep coming up for very specialized tasks. You don't want to be handling every single parameter by hand. That would be very, very unwieldy. So Flux has this very handy dandy params function, which can, bring all of these parameters in one place together. So you don't really have to ever deal with any of these things. These are very basic things that any machine learning platform worth its salt would provide use for. But then you would ask me, well, I wrote a linear function here. How does Flux ever know what you know parameters that this has? And the answer is that all the parameters are just the inputs to the model, right? So your x, w, and b will be what we will treat as parameters. And in case that you want to treat the parameters more carefully, for example, so for example, if I assign W as, say I choose the same weights, right? So Control C, hopefully that works. Yep. And bias. Yep. So this works as well. So now if I want to have, so notice this is just regular arrays. This is not associated with my Flux model at all anymore. But if I still tell Flux to, uh, collect the parameters from from W and B, we can just do that and it would work the same way as before. Um, Another thing that we would want to do is define a loss function effectively, right? And earlier, how we had been defining it was a bit unwieldy. Um, you would remember defining, where did we go? Yeah, there it is. So sum over all the labels and the predictions and then square and all of that. Well, that's essentially the squared loss, right? The squared error. And typically in ML, what is preferred is we aggregate over certain statistics. And one thing that is done fairly commonly is the mean squared error or the MSE. So Flux has this handy dandy flux.mse function as well. Um, of course, you can just ask for help for any of these functions and it will give you exactly what it is trying to do. Uh, so this comes from a different package, but like this will tell you that it comes from the losses. And you can use either of them, right? It makes no difference. And that's sort of the beauty of Flux, that it can compose very elegantly with the rest of the ecosystem as well. Um, so let's say I define my loss as between X and Y, and it would be flux.mse. Typically, I will have a model, and this is how we saw earlier. You know, this is how we called our model with a random input. So this is how we would define our loss function. In this case, let's say my dance is another 2, sure. Um, cool. That was very easy, right? And the next thing that we have to do, as we saw earlier, is to calculate the gradient. Um, let's first instantiate our data set first. So let's say I'm taking a random sample. I'm creating a matrix which has 2 inputs and 4 data points. So that's how I'm, structuring my data itself. So this is fairly common in Flux that we typically, have our uh, data stored in W, H, C, and N. So this is your width, height. So this is for an image, right? Number of channels, so the number of channels you have, and the end, the batch size. So the batch is generally at the end. This is in contrast to how something other frameworks treat it, and you would find that the reason for that is that Julia itself is column major, which is again different from how different languages treat it, which means that we can get a lot more benefit out of treating the slowest um, the slowest iterator at the farthest end in some ways. And the batch will be the slowest iterator because if you do the transform over everything. And it also means that we can parallelize really easily. So this is just an artifact of how the language itself is structured. Um, so we have X, right? And now let us calculate the loss. So oh, first we need our data points. So let's say I do rand 0, actually this would work just fine. 2 comma 4, right? Cool. Actually we want, let's try again, should be fine. All right, that works. Actually, no, we want just one output, right? That's, yeah, much better, much better. So now what we can do is call loss on our X and Y and see that we in fact get some sensible loss out of it, right? Uh, any questions so far? How we've set up our problem thus far? So we've, just to recap, we've made our 2 inputs and 1 output model. We saw that we can, use the flux.params function to gather all the parameters. We saw that, we can also use completely user-written code, just the same way as we would Flux code. We saw how we can use the loss function, and then we calculated the loss itself. Is everyone with me so far? Any questions? All right, seeing none. Let's move further. So now that we have our uh, loss function in hand, we want to calculate the gradients, right? And to do that, I showed this a little bit earlier, but we use a gradient function. And what we want to do is we give it a no argument function. In this case, we just don't have to, but in other cases we can. Loss x and y, and then flux.params of model. Does that sound good? Oops. And we'll have to now get this grads object back, and this is a little bit different from what I told you earlier, that we don't really deal with custom types. Like we completely support user defined custom types, and we actually do encourage people to write their own layers because of just the wide gamut of problems that people solve, that you can always have uh, you know very general layers written. So for example, your convolutions, your normalizations, LSTM, so on, linear layers, and even different types of those. But as growth comes, you will find much more, not just complicated but specialized layers come in to solve specialized problems. And I'll show you a little bit how we can actually make it so that you can use completely custom code, absolutely no flux involved, to also be used as if it was completely flux code. Um, but I also told you that we generally expect people to, have very normal types flow in their program. And as you saw earlier, the weights themselves, they're not any special type, they're just an array. So like if I were to ask Julia the type of the weight, I would say it's just a normal array. So what is this grads object doing here? So this grads object is not that special actually. It's just keeping track of all the parameters and the corresponding gradients. Um, so let me show you another trick really quickly. Um, let me take gradient. Um, Linear, yeah, let's give it linear. And in this time, let's say linear x m dot w and m dot b. So notice, all right. Um, so this sum, essentially this circle and this sum is a very simple way of doing function composition. So f circ g is essentially the same as f of g of x or whatever, right? So that's all that that's doing. So you would notice that this time you got a tuple out. And I would now show you that gs m dot w is essentially the same as uh, this gradient right here. Um, it'll be slightly different because you need the x values to be the same, because they wouldn't be, but in general, you would get the same exact thing. Where did that m dot w go? Yeah, there it is. So you have this m dot w thing, and you have gs m dot w. So if you want to get the gradients for the model out, you can just treat it as a dictionary and index it with the parameters that you're interested in, and will check out the gradients for you. So that's very exciting. It means that we can calculate the gradients very easily. Flux uses internally this thing called automatic differentiation. Its automatic differentiation is called Zygote. This engine is called Zygote. It is an area of very active development, as well as what makes like language-wide differentiability possible. So no matter what kinds of weird types, what kinds of weird code structures, and custom code, user-defined code, whatever, we can handle that. Of course, there's always progress to be made in these things in these fields, but it means that by and large we can treat any user-defined code as differentiable. Um, all right. Now that we have the relevant gradients, we have to now train the model. Now, earlier someone had asked me, well, what happens if there's two minima? How does our machine learning model ever know where to pick, and like how to avoid one or aim for another one? And the answer is that it doesn't. It just doesn't. Without using some specialized tricks. Now, be that in the form of you know clever assessments of the loss surface beforehand, or by using global optimization routines, or by other optimization routines like stochastic gradient descent. So earlier, what we saw was gradient descent happened at every little step, right? But that might not always be the case that we want to do that. Essentially, because you would have some data points that are just not that interesting, knowing that you're already reached somewhere. Plus, what you need is you want the average case to be a lot more optimal than just the most ideal case. So for that, you want to use something called stochastic gradient descent. Now, what is the difference between gradient descent and stochastic gradient descent? Well, in stochastic gradient descent, we sometimes arbitrarily just drop data points that we don't want to train on. This basically means that we're choosing the data points that we will essentially train on. And what that means is uh, more than anything else, it means that we will not be biased by one large group of data points. Um, you know, having some optima, it may not be the global optima, but a stochastic gradient descent will ensure that you never really get stuck in those saddle points. However, that can still be like a possibility where you are dealing with very complicated loss surfaces, at which point in time it is of course expected to use even more clever techniques like global optimization routines. So that's all well and good, but that's also pretty much what's it called, orthogonal to today's session in some ways. Um, what we want to see is how do we train our model, right? Just excuse me a second here. Yeah, there you go. And there you go. Perfect. So what we want to do is we want to implement a stochastic gradient descent. And as I said before, it's the essential same thing. So we have a for loop and we can let it go from 1 to some in. Let me write this function down. SGD. We can, first of all, we'll have to take the loss, right? We'll need the inputs. We'll need the labels. Let's start with that, right? Let's start with just this much. Um, oh, and we'll need the epochs. Let's say we start with 100 or something. Sure. So for I equals 1 to n for epochs, we want to choose certain data points. We don't want to use every single one of them, right? So we're going to choose something like I equals, let's just make this nothing. We don't really need this yet. Rand, let's pick 10. Yeah. Let's just pick one data point, right? Like let's make it easier on us. 1 to length of XS. Note that our data set XS equals x1, x2, x1, x2, and so on, right? So this is how our apples and bananas are stored. So like the red value and the green value, yeah. So we pick just one, that's fine. And since we have the model which does one, like 2 inputs and 1 output, right? So it handles only one. What we will see is that we don't really have to do it like this. We'll see a much more efficient way in just a little while. So we can see x train equals x of I, excuse me, and y train equals y of I. So we had y's and x's, so sure. So now that we've picked our training model, let us also ask for the params, and that way we can do this loss xy and right. So you would notice that this is following very simply the same pattern as in here, right? Next thing that we have to do is the update step. So Flux also allows optimize.update bang. So you have your optimizer, your params, and your gradients. We don't have the model, we don't really have to worry about it either. We will ask for the optimizer as well. Cool. So one thing that I would want to see, just to make sure that we're doing things correctly, is our loss. So this is just we can monitor, how our loss is doing. So loss function, earlier we defined this, we have M. Let's define PS as flux dot params of M. And after that, we have Y's, we have our X's. So we're ready. SGD. Oh, we have to define our optimizer. So let's go with the simple gradient descent optimizer, right? So that's the stochasticity is now built into our training regimen, essentially. So SGD, loss, params, X's, Y's, and opt. Cool. And as we see, our loss has in fact, gone from 0.3 to where is it, 0.6, 0.16. That's exactly what we expected. That's brilliant. We are in fact converging. Now I don't really want to see what happens if we do 1,000 of these, but sure, I guess we can do that. And our loss value seems to have come, to a basic stand at 0.02, which is by no means ideal, but it works just fine for a training problem. And now what we're able to see is our model itself right here. So remember that the last few samples were from bananas and the first few are from apples. So if I were to take the first sample and I would push it through my model, I would get 1, which is, was it an apple or a banana? I forget. Oh, okay, yeah. So let's see y's of 1, 0. Oh, so it has actually done pretty poorly on that one. Yep. So our model is in fact not trained that well. But the trick in these cases is, again, we just need to train it more. And you would see that more often than not, you will end up with a perfectly trained model as well. Now, I did promise you that, we wouldn't be doing just this. What we want to be able to do is we want to be able to, not have to write so much, function. Yeah, we don't really want to be writing all this much code. Of course, we can, and it's good that we can. Essentially because we can have very, very complicated training regimes and still be able to support it out of the box. But in general, for very small problems, we don't really need that. So if I have my dense layer right here, um, I have my y's right here. Yep, that's all good. So let's see what X apples is, right? So let me do this, reduce vcat X apples. Oh, wait. Oh, no, that one's from my bad. So your X apples needs to, first of all, we'll have to load that back in, which is, oh, never mind. Yeah, there you have it. So rather than doing this, what we will do is we will take each row of apples, and we will make a matrix out of it. apples. There you go. And just like that, we can, vcat. So this is just concatenating it vertically, right? And the matrix function is just creating a matrix out of those two, how do you say it? The columns, bananas. And this is how we would represent our x's now. So m x's. We need to transpose this as well. Transpose and collect. Yep, there you go. And here you have it. So this is our entire training set in one place, right? So let me make my data set. So in most cases, what we would do is we would, as I said, shuffle our data set, would augment it, all of that good stuff. But right now we're doing something very simple. So I would, just call this as my data set. So this is a very crude way of making my data set, but it works nonetheless. Of course, you can also use flux.data.data loader and create the data set that way. So we can do that as well, actually. Let's do that. Right, so you have your data right here. Next operation of interest is the flux.trainBank. So this way, we don't really have to write any of the loops. We don't really have to write much code at all. And optimize. So in this way, we can train on the entire data set, and we can even give things like at epochs 100 or like 10. So you have 10 epochs, and that's how you've trained it. You've trained your model on 10, separate training sets, 10 on the same training set 10 times essentially. You can even give it callbacks. You can do a bunch of different, tweaks and such to get your training routine just right. And now if we, see what our model looks like. Excuse me, dude. Yeah. Right, I wanted the second row. Oh no, it's transposed matrix, right? So I need columns. Yep. Uh, yep, now it's much better, right? We are able to see that our bananas are actually classified as bananas and our apples are actually classified as apples. So that's incredibly, satisfying. Allows me to take like a moment's breath to make sure that our models are actually trained properly. And yeah, that's exactly how you create a very simple, neural network with Flux. And of course, let me point you back to, some of the, um, more complicated models that we, have and we work on. So if you go to fluxml.ai, you'll be able to find a bunch of the, where people are using Flux, not just on pretty old list. Actually, we have to add many more folks on this, but where all Flux is being used. So like on probabilistic programming, on differentiable programming, on 3D modeling. Um, so yeah, lot to speak about in just this one area as well. Um, so yeah, so I think the final leading thoughts that I would have for you are so far we've just used two features. How would we actually expand our knowledge of what features to use, what would be a good feature, and how do you actually generate more features? This is something of very high importance for very complicated problems, right? Because one thing that you would never really know is the kinds of loss surfaces that you're dealing with, right? So it's very important for us to be able to feature engineer just right so that we're not, wasting compute or, focusing on the wrong problems. Um, we have many other options, so like train a neuron with a third input. And can you find a good way to visualize the result? So I'll leave that as an exercise for the reader, but again, there's many ways to actually visualize your training as well. So with that, I have about 10 minutes, actually 5 minutes for question answers, and I'll be happy to take some up, um, you know, and help you guys um, work on that. Can you explain Zygote? Absolutely. So uh, many and actually most modern machine learning platforms use this technique called automatic differentiation. And actually, I believe it is planned that Matt will show you, some features of what automatic differentiation is actually. And automatic differentiation in Julia is implemented by one of the packages that implements is a Zygote. So Flux uses Zygote as its AD engine, and what it provides is essentially being able to differentiate arbitrary Julia code. So it means anything that IOU write can be differentiated. So for example, as just so for example, x squared plus sine of x times y plus y squared or whatever, right? Like, I don't know. It could be a significantly more complicated expression than that for sure. But so the gradient function actually lives in Zygote, and if you have different types. So for example, oh yeah, let me show you how. Um, so let me finish my thought here. So you have uh, gradient over this function. So of course, this function can be any function, um, but Zygote will allow you to calculate gradients over these based on some input parameters. Further, you would want, arbitrary types and, very complicated types especially. So let's say I have my type and I say A, um, yep, B. So let's say this is a type I defined, right? And let me define base dot plus my type. X can just be defined as my type A dot A plus X. Actually, let's not do it. Just make it a bit more complex, right? Why not? B dot A dot B plus B dot B. This thing can be my type. And now if I have A as my type, rand 3 comma 3, and two of them on type, and B, so I can do A plus B. And now I can use import base no necessary. So let's do gradient over A and B, do A comma B. I can do A plus B. Oh, sorry. Let's say I'm calling it some temporary t dot A. I want the sum. I don't know. I'm just making something up. So this thing will in fact, be able to differentiate through all of it. And what it finds is that in our gradient computation, it never really need the value of B was just never necessary, and then it was able to determine exactly what the value of the B field essentially. So if you wanted to make that happen, we can do something like sum t dot b times, I don't know. You could imagine how you would want to fill this up, right? But it allows you to take gradients of completely arbitrary code. And the same thing if you wanted to turn into quote unquote a flux layer. So this is as long as you can take the gradient of it, it is already a valid flux layer. There's nothing stopping it from not being. But one of the more typical ways that we would also do it is called flux.addFunctor. So we would, uh, make my type available to Flux as a layer essentially in some manners of speaking. So when we do that, when I do flux.params over A, as you can see, I'm able to gather all the parameters from A and use it as any layer in Flux. So it's just as simple as having your own types or basically containers for parameters or just regular inputs. It makes no difference. So that's a very quick rundown of what Zygote is from a high level. Matt will talk a little bit more about what automatic differentiation is. It's again an area of immense research and interest recently, especially with differentiable programming becoming such a big deal. So yeah, thank you for the question. Any other questions that I could help answer? Otherwise, that was the first day of our ML training, and hopefully you guys were able to learn something. I had a bunch of fun, uh, and do hit me up if you guys need any clarifications on anything. You can find me on the different means that you already know of. So be that through email or on GitHub website, however, on Slack, feel free to get in touch. I'd be happy to help you guys out. Um, Other than that, it's been really good. Thank you. And looking forward to day two. I hope you guys are as well. Um, I'm sure Matt will be back for tomorrow's session, so keep an eye out. Thank you. Thank you all.